So we're going to go back to talking about capacitors. We're going to talk about them again in the future, by the way. These are really important. They store charge, they store energy, they're used as switches in electronics. Cell membranes act like capacitors, so if you're studying the human body, you've got to know about capacitance. I mean, this is just important stuff. Okay, so here's a capacitor. So this plate has a positive charge. This plate has a negative charge. So what's the total charge of the capacitor? Well, it's 0, okay? All right, and that's true for any capacitor. So it's kind of useless. I mean, if you said, what's the charge of a capacitor? 0. Okay, that's true, but useless, right? So when you talk about the charge of a capacitor, you're actually saying, what this is, okay? What this is, all right? Okay. Okay, so if this is a plus charge and this is a minus charge, that means there's a potential difference between the plates. Agreed? Like I showed you earlier. All right? Okay, so there's a potential difference between the plates. Now, here's just a little logical argument. All right, so the potential difference between two parallel plates of a capacitor is my friend Ed, the talking horse, right? The E field times D, where D is the distance from the negative plate. All right, now, would you agree that the E field is proportional to the charge? Well, of course, right? Charge creates the E field. If it's a gigantic charge, you're going to have a gigantic E field. If you have small charge, small E field. I mean, depending on the distance, of course. Okay? So the E field depends on the charge. No kidding. Well, if the E field depends on the charge, so does the potential difference, right? So, all right, so, okay. So obviously, if this is true, that the potential difference also depends on the charge. And no kidding. That's, I mean, right there, right? If E depends on Q, then delta V depends on Q. Okay, now what did you learn in math about statements like this? It's a proportionality. We've talked about this before. It's a proportionality. So we don't like them. We want to put an equal sign here, right? It's like if you work at the PCC, the money you make is proportional to the time. Well, no kidding, but that doesn't help. That doesn't help you plan a budget. What do you need to know? You need to know how much money you get per hour, right? So the money is equal to the hourly rate, $10 an hour, times the time, right? And now if you know this, you can plan your budget. Okay. So, we don't like it. We want to change this. So this here is the same thing as saying that delta V equals some constant, like the hourly rate at the PCC, times Q, right? Okay, well, that's cool, but I don't like it. And you'll say, why? Let's turn it around. I mean, if this is true, isn't it also true that Q is some other constant times delta V? Well, yeah, I mean, 6 or half a dozen, right? All right, so we want to look at that. So what's the constant? So it turns out that the constant is the capacitance. Okay? So this is kind of like the F equals ma of capacitors. The charge on a capacitor equals the capacitance times delta V. Now wait a second. The C is a what? It's a constant. All right? That's the important thing. It's a constant. So what does it depend on? It depends on the geometry of the capacitor. That's all it depends on. You'll see. Okay. So like I say, this is like F equals ma, right? Q equals C delta V. So you should walk around campus. Well, you're not here, so you can't. But walk around your house or wherever you are. Q equals C delta V. Q equals C delta V, So Q equals C delta V. C is capacitance. It's a constant for a particular capacitor, right? For a particular capacitor, it's a constant. Okay, now let's look at the units. Okay, so solve for C. So C equals Q over delta V. Okay, what's the charge of Q? Coulombs. Too many C's. Oh golly, hey, I'll write it. Coulombs. What's a sign of units of voltage? Volts. All right, so we would be perfectly happy saying that capacitance has units coulombs per volts, but you know, we get all these dead physicists we have to honor. So it's called a farad after Mr. Faraday. Okay, Faraday. All right, so capacitance is measured in farads. So if you have a capacitance meter, which you will in lab, and you know it's going to measure so many farads. Okay. Now, so capacitance is the ability to store charge. So anything that can store charge has capacitance. So, you know, like if I walk around in this, just pretend I'm in Arizona in the desert, right? If I'm walking around, you know, like this, and I'm, you know, rubbing my bottom of my feet against the carpet, I'm going to store charge, right? So I would have some capacitance. Okay. This is the formula for the capacitance of a given capacitor. So look at, there's our epsilon zero again, that constant that you always see with electricity. This A is the cross-sectional area, and the D is the distance between the plates. So that's what I mean. For a given capacitor, it's a constant, right? Because constant, that doesn't change, that doesn't change. All right? So it doesn't depend on the Q, it doesn't depend on the delta V, it just depends on the physical characteristics of the capacitor, because it's a constant, right? That's why I made such a big deal about that. It's a constant. Okay. Consider a simple parallel plate capacitor whose plates are given equal and opposite charges and are separated by a distance d. Suppose the plates are pulled apart until they're separated by a distance uppercase d, which is bigger than lowercase d, all right? So you're just taking this parallel plate capacitor and you're pulling it apart. Now careful, again, read these words. Again, man, if I was taking this test, I would underline this, you know? That's why people make mistakes, because they don't read the questions carefully. The electrostatic energy, in other words, the potential, the electric potential energy stored in the capacitor is what? Greater than, same as, small than, before the plates were pulled apart. So think about it. I have positive plate, negative plate. Here they are initially. Where do they want to be? Like that, right? So here they are initially. Now I'm doing this. What's happening to the electrical potential energy? Okay, so pause your video and figure it out. I hope that should be obvious, right? It's like lifting weights. You know, the plus and the minus, they want to be together, but we're pulling them apart. We're putting them in a situation where they don't want to be. It's like lifting weights. So you're increasing the electrostatic potential energy. Okay, remember, these questions are sometimes designed to trick you, so you got to be careful. For any capacitor, Q equals C delta V. Consider a parallel plate capacitor. If the charge Q on each plate is doubled, what's the effect on C? Well, pause your video and figure it out. Okay, what's C? It's a constant, right? It only depends on the geometry, the physical makeup of the capacitor. Right? Look at the formula. Does it depend on the Q or the V? Not at all, right? Okay, so if you double the Q, who cares? It has no effect whatsoever, right? Okay, the C doesn't change. But what would change? So C doesn't change, right? So if you double the Q, what else has to double? The delta V has to double. Okay, that's all. All right. You know, we generally show these parallel plate capacitors like that. But in the real world, you don't really see a whole lot like that. What you see in the real world are these cylindrical capacitors. All right, so this is a cylinder, right? And this is a cylindrical cylinder, right? This is air, or, well, whatever. I'll get to that later, okay? This is metal, this is metal, this is not metal. And so you have this charge plus, this charge minus, E fields go like that, all right? And you have equipotential, you know, circles, right? So it's a spherical capacitor, okay? If you ever look in any kind of a circuit board, you see gobs and gobs of capacitors. See these blue things? These are capacitors. These are resistors. We'll learn about these as well. All right. But all I'm saying is, take anything apart that has a circuit, electronics in it, and you see lots and lots of capacitors. Oh, okay. Now I'm actually going to do a demo. Let's see. Let me erase this. I don't care. Okay, so here is a metal plate. Here's a metal plate. I have these tiny little pieces of plastic. I don't want this metal plate to touch this metal plate. I'll explain why in a minute. All right, so, just a little tiny thing, just 1, 2, 3. All right, so look at, what did I just make? A capacitor, all right? So here's a capacitor meter. So I'm gonna measure the capacitance, okay? So here we go. Okay, so the capacitance is 0.4 nanofarads. Okay, so the capacitance is 0.4 nanofarads. Pretty small, wouldn't you say? All right. Okay, so now what I'm going to do, I'm going to take these little spacers out of here. And this is the same material as the spacers. It's the same thickness, but now I'm going to put it there. Put it like that. So like a sandwich, right? Okay. So now I'm going to measure the capacitance. 0.87. Okay, so what do you notice? When I put a piece of some kind of plastic in the middle, look at it. The capacitance increases. Now that's awesome, right? But not just that. Think about it. If this were a real capacitor, well, the way it is, but like if this is charged plus, this is charged minus, what do they want to do? They attract, right? Well, I don't want them to touch each other because that just wipes out the capacitor. So in a real world, I got to keep these things separated, right? So how do you keep them separated? By putting something inside, in between, okay? So this plastic thing, it keeps them separated, which is what you want, right? So you want that, but then you get an added bonus. The added bonus is it increases your capacitance. Now, if that's not a win-win, I don't know what is. Okay, so let's talk about that. So when you put something in between the plates of a capacitor, the thing that you put in between them is called a dielectric. So, just like it says, or sounds, dielectric. Oh, wait a second, I gotta make sure I spell it right. Yeah, so dielectric. All right, dielectric material. Okay? All right, so, and by the way, that was a piece of plastic, right? Is that a conductor or an insulator? It's an insulator, agree? Okay, so when you put an insulator in between the two parallel plates, you have a physically stable capacitor, and it increases the capacitance. So it's awesome, right? It's awesome. So you usually put a little zero here when there's nothing between them, or there's air, then this is with something, Okay, so the question is, why did the capacitance increase when I put that piece of plastic in there? Right? Why? We should be able to explain it, Well, we can. So here's a capacitor, right? Parallel plates, plus, minus, uniform E field, E0. Voltage is my friend Talking Horse, Ed, right? So it's E0D, okay? That's D, All right, so this is nice, everything's wonderful. Okay, now this is the dielectric. It's an insulator, right? Well, what's an insulator? Like a plastic. It's made out of maybe polarized molecules. What did we learn about polarized molecules in the previous chapter? In the previous chapter, we learned that, in nature, the polarized molecules are randomly distributed. But when you put them inside, with an E field, then they line up, right? Why do they line up? This formula I keep talking about all the time. I tell you, we use it so often, okay? So the E field is in this direction, so the plus piece is going to go that direction, and the minus piece is going to go that direction, So look, here they're randomly distributed. Now they get inside the E field, and bingo, now they're uniformly distributed, right? Okay, so let's say this piece of plastic, this dielectric, is completely inside. Okay, now remember, the E field of the capacitor goes from plus to minus, right? E0. But whoa, wait a minute. Look at these polarized molecules. Now we have E field plus to minus, that way, plus to minus, that way, okay? So the E field of the capacitor is this way. The E field of the polarized molecules is that way. So we're going to have a partial cancellation. Agree? So we're going to have a partial cancellation. So these right arrows is from this. These left arrows are from this. And now we have a weakened E field, right? This E field here, E, is less than what we started off with. Okay? So the E is less, this E field now is less than the original E field. Okay? Now remember, the potential difference is ED, right? ED. So this new potential, which is ED, is less than what we started with here. Agree? So the E field has decreased, and the potential has decreased, right? Well, remember, Q equals C delta V, F equals MA. So therefore, C equals Q over delta V, right? And I know, okay, so C is a constant for a given capacitor. But now look at what's happened here, though. What's happened here is that this thing here, this delta V, has decreased, right? Decreased, right? So we've changed the capacitor. We've changed the physical characteristics of the capacitor. So this has gotten smaller. This is the same. This has gotten smaller. If that's the same, that's smaller. What happens to this? It gets bigger, right? It gets bigger. So that means that C with the dielectric is larger than C without the dielectric, okay? Like I showed you, all right? So how do you do that? How do you describe that mathematically? Well, it's simple. So a little while ago, I said that for a capacitor, for a parallel plate capacitor, the capacitance is epsilon naught A over D, right? Now, when I said that, I didn't tell you everything. So this is assuming there's just air between the plates. Well, usually there's not air, because how are you going to hold this silly thing together, right? And so when it has a dielectric, you just multiply it by that. Okay, now that's not a K, it's a kappa, right? Kappa, right? So kappa is called the dielectric constant. So it's bigger than 1, yeah? So, so if you're multiplying this by kappa, you're increasing the capacitance, right? So some people write it like this. Some people write it, the capacitance equals kappa C0. So C0 is just the epsilon naught A over D. That's like the capacitance with just air. And then this is the dielectric constant, okay? So basically, that's all you do. So here are some dielectric constants. So this is dielectric constant. This is the dielectric strength. This is like if you exceed this, the thing breaks, all right? Okay, so like vacuum or air, basically 1. Teflon, 2.1. Paper, yeah, paper, 3.7. This might surprise some of you. Pure water is not a conductor, okay, pure water. Regular, ordinary tap water is because of all the junk in it, right? But pure water is actually an insulator. Look at the dielectric constant, 80. That's cool, right? Then you have these crazy things. Titanium dioxide, 110. Strontium titanate, 300. Think about it. So that increases the capacitance by a factor of 300. That's incredible, right? It's probably super expensive, but anyway. All right, so basically, with all of the equations that deal with capacitance, if you have a dielectric, you just multiply everything by this kappa. And it all works out, so that's not a big deal. Okay, let's talk about a battery in a capacitor. So this is an uncharged capacitor. So let's say we have this uncharged capacitor just sitting there minding its own business, and then we just attach a battery to it. Okay, and it's a working battery. All right. So what's going to happen? What's going to happen when you connect the battery to an uncharged capacitor? Well, you're going to charge the capacitor, right? There's going to be the flow of charge. And what did we call the flow of charge? That's current, right? And remember, we're talking about conventional current. Okay? So there you go, all right? So this is connected to the plus, so it's going to become positively charged. It's connected to the minus, so it's going to become negatively charged. Okay? Now, so basically you connect this battery to this uncharged capacitor. It's going to start charging the capacitor. Now remember, these guys don't want to be there. They repel each other. These guys don't want to be there. They're repelling each other. So there's only so much room, let's just say, it's only so, this can only hold so much charge. Eventually it's going to say, enough! It's kind of like Hawaii with the tourists, right? All right, this can only hold so much charge. Okay, so eventually, when the capacitor is fully charged, what's going to happen? What's going to happen to the current? Stops, right? I'm done. I don't have any more room for you guys. Go away. So the current is going to be 0. All right? 0. Now, I'm not supposed to see that yet. When the current becomes 0, so let's say this is 1.5 volt battery. What's going to be the potential difference between this plate and this plate? Guess. It's going to be the same thing, right? It's going to be the same thing. All right, so what I'm saying is when you charge an uncharged capacitor, you're going to get current, and you're going to charge up that capacitor, but you can only charge it up so much, and when it's completely full, the current stops. And at that point, the potential difference between the capacitor is the potential difference between the plus and the minus of the battery. Simple as that. I think that makes sense. Okay. Oh yeah, here's kind of a cool question. So this is a point charge, and these are just equipotential surfaces, all right? Okay, what is the sign? This is like a review question. What is the sign of the work done by the electrical force to move a charge along an equipotential surface? So let's say, from here to here, from here to here, or from here to here, something like that, Right? The potential is the same everywhere along this surface, right? So how much work does it take? So pause your video and figure it out. Okay, I hope you remember 0, all right? Because the potential difference is the energy over the charge, but energy is work. And remember, it's potential, it's an equipotential surface, so this is 0. So that's 0. So that's 0. So everything is 0, okay? So this doesn't take any work, right, to move along an equipotential surface. Now keep that in your head. Okay, keep that in your head. Okay, you read that while I erase. Okay, so metal 1, remember these are metal, right? Conductors. So metal sphere 1 has a positive charge of 6 nanocoulombs. Metal sphere 2, twice the diameter of sphere 1, neutral. Then we connect them with a wire. What are the final charges of each sphere? Okay, what's the principle? Well, metal, metal, metal. So what state are they going to achieve? Well, electrostatic equilibrium, right? Okay, so what is the work required to move a charge along an equipotential surface? 0, right? So what's the work required to move a charge along an equipotential surface? 0. So that means what has to be true about the potential here and the potential here? They have to be the same. That's the key, okay? Some people read this and they don't really analyze it. They just say, well, you know, the charge per unit surface has to, the charge per surface area has to be, or whatever. Or sometimes they just say that the charges, they say that the charges have to be equal. Why is that? Where'd that come from? The fact is that the potential has to be the same. Okay, the potential has to be the same. Well, what's the potential for a sphere? KQ over R. All right, or D or whatever, I don't care. All right? So what we're saying then is KQ1 over R1 has to equal KQ2 over R2. All right, but it says that R2 is 2R1, right? I guess I should just say that. All right, so there. Okay? That's not good, right? Okay, so therefore, get rid of the K's, right? Multiply top and bottom by 2R, divide by the R. So what does that say? It says Q2 equals 2Q1. So the charge here has to be twice the charge there, okay? So Q2 is 2Q1. Well, we started with 6, so how do you split that up? Remember, charge is conserved. You can't just grow charge, okay? So we have 6 to start with. Q2 is twice of Q1. So let's say that Q1 is 2 nanocoulombs. So 2Q is 4 nanocoulombs, right? This is twice of that, and you add them up to get to 6. But the whole point of this problem is just to remember that the potential here has to be the same as the potential there because it's connected by a wire. Okay, so we've talked about a capacitor stores charge, right? In 2 ways, you know. All these positives don't want to be there. All these negatives don't want to be there. These are attractants, so they want to be close, but we're keeping them apart. So, you know, there's a lot of charge being stored. There's a lot of energy being stored. Okay? So, so this is just a formula. Sorry. So this is how much energy is stored in a capacitor. So the energy, the electrical energy stored in a capacitor, Q squared over 2C. And if you don't like that, you can just say that Q equals C delta V, right? So you can just substitute, and you can use that formula, right? That's what I'm saying. Okay, what's F equals MA? Q equals C delta V, right? That's F equals MA for a capacitor. So the equation is UE equals Q squared over 2C. And that might be good for your problem if they give you the Q. But if they don't give you the Q, you have to substitute. Let's just substitute. So we're going to have, square that. So C squared delta V squared. Then on the bottom we have 2C. So this C kills that C. And we just have C delta V squared over 2. C delta V squared over 2. So, all right, so, you know, if you have a homework problem, they talk about energy stored in a capacitor. There you go. Okay? What can I say? Now, what I'm going to show you next is just interesting for history reasons. That's all. Okay, so, you know, when electric fields, and we'll learn about magnetic fields later on, but when electric fields and magnetic fields were first thought of, they were just thought of something to help people sort of like visualize things. Nobody thought that they were real. But then people were working with capacitors, and somebody figured this out. And then somebody said, well, golly, I wonder what the energy density is. Well, what in the world is that, right? Well, what's any kind of density? What's the mass density? It's the mass divided by the volume, right? So the energy density of a capacitor is just the energy divided by the volume of a capacitor, right? You know, just energy density, all right? Whoopee. Okay. So anyway, so somebody worked it all out. They did a whole bunch of math, which I'm not going to repeat. And they came out with this equation. 1/2 kappa, there's our good old kappa, right, for the dielectric. Epsilon 0 times E squared. Now, whoever came up with this was like, whoa, why? Well, come on. Energy density is energy, right? Energy per volume, but come on, it's energy. And energy is real, you know? So the energy, or the energy density, can be written in terms of the electric field. So if this is real, which it is, what does that say about the E field? It has to be real, right? And so this equation sort of blew everybody's mind, because it forced them to realize, hey, this is just not some figment of our imagination that we use to kind of visualize stuff. This is something that's real, you know, real. When we talk about magnetic field, we're going to have something similar to this. So like I say, it was kind of a big deal. So later on, we're going to see that there's energy stored in a magnetic field as well. So again, this is just history, all right? We're never going to use it, I don't think. It's just history, but it was important back in the day, all right? Oh, yeah. When do you have to leave? 3. Okay. All right. So everybody, please watch this. You know, we've talked about capacitors, and this is just a short video. It's about how particle accelerators work, and it will give you a really awesome example of the importance of capacitors. So just watch it. It's really awesome. Okay, so this is what we had to do. That's what we learned. Potential energy, electric potential, conservation of energy. We learned the potential of charges, spheres, and capacitors. We skipped that. We learned about the connection between potential and field. And we learned about capacitors and dielectrics. And let's just quickly review it. Well, the charge can be thought of as creating E fields or scalar V fields. And that's how they're related. We learned electrical potential energy depends on charge and location. We learned how a battery works. Not really, but we talked about it. This was a nice problem because it used conservation of energy, which is incredibly important. So you better understand that. I mean, it's important throughout all of science. We learned about this unit, which we'll use more and more, called an electron volt. It's just much easier to use than joules. The potential of a capacitor. Don't forget this crazy definition, right? The distance starts at the minus. The potential of a point charge. The potential of outside a sphere, same formula. The E field or capacitor. Conductors in electrostatic equilibrium, that the voltage is constant inside. And the capacitor, constant for a given capacitor, right? It just depends on the geometry of the capacitor. And this is the kind of capacitor you see in the real world. And this is the very important equation, like F equals ma for capacitor. And that's it. Thank you. I forgot.